Hi everyone, I welcome you all in the next lecture of quantum mechanics. So in previous lecture, we have already, uh, understood the concept regarding the, particle in 1D box, and where you can see that this particle was, confined into infinitely long wall, and the potential outside the wall was infinity, and the potential inside the wall was zero. And due to this reason, I have divided this particular problem in three different regions. And at x equals to 0, the wave function will be 0 because there will be zero probability of finding the particle. And then again, at x equals to a probability density will be 0. That is the same region, right? And then we have solved the Schrodinger equation based on, in the region 2. And after solving, we have seen that we have calculated the wave function using the boundary condition, right? And from there, we have calculated the quantized form of energy like n square pi square h cut square divided by 2ma square. And here is the energy diagram that we have already seen that we have calculated the ground state energy that was E1. E2 is the first excited state, E3 is the second excited state, and so on and so forth, something like that. So this is called as the discrete energy level. Now, next thing was that, so finally, from here we have used the normalization of the wave function, and after using the normalization, we have calculated the, wave function that was a function of, x and t. And that is called as the quantized wave function, that is root 2 by s, and that was sinusoidal in x domain and, exponential in, time domain, that is e to the minus I omega t. Okay, so in today's lecture, we'll see that once we get the normalized eigenfunction for the wave, that is this one, and then we can, plot this value. So here on y-axis, there is a wave function, and on x-axis is the position of the particle. And what we observe here is that at x equals to 0 and at x equals to 1, this is, complementing the boundary condition, that means size 0 at x equals to 0 and 1. And this is happening due to, at the boundary, uh, there is a zero probability of finding of the particle. And then we can, plot this wave function with respect to x for n equals to 2. And then what we see here is that it basically gives you a complete cycle of sine wave kind of thing, right? And here what we see here in the middle of, the box, you will see the probability of finding of the particle is 0 as well. Right. So, and also you can see for n equals to 0, we are getting half sine wave. For n equals to 2, we are getting a full sine wave, something like that. So if you are increasing the n, then, oscillation is increasing. So let's say we plot the wave function for n equals to 3, and what you see here that initially at x equals to 0, the particle size 0, and then at x equals to 0.25, at x equals to 0.75, at x equals to 1. So particles finding probability of wave function is 0. That means if you are increasing the value of n, then what is happening, it is inducing the oscillation. So more oscillation will appear. That can be, demonstrated from this particular graph. And this one is the, complete graph for n equals to 1, 2, and 3, something like that. So basically what you observe here, this results basically tells you as n increases, number of oscillation increases, and, number of nodes increases. So what is node? Node is where the probability of finding of the particle, or where the wave function is 0, that is called as the node. So here you can see this is peak and this is called as the node. Sorry, here this is the wrong notation. Node will be at x equals to 0.5. Here node will be at x equals to 0, at x equals to 0.25, at x equals to 0.75, and at x equals to 1. So basically, what is happening, the wave function becomes 0 at the boundary due to, obviously due to infinite potential walls. And, quantum confinement leads to, discrete allowed quantum state that we have already seen. If you vary n, then definitely you are going to get the discrete quantized state instead of continuous classical motion that happens in the Newtonian mechanism. Okay, now coming to, probability density of particle in the box. So basically, what is probability density? So probability density can be defined as a modulus of psi of xt square, and this basically tells you the probability of the finding of the particle at a given position. Is that clear? So here, if we plot the probability density on y-axis and position on the x-axis, here you see that probability density of the particle for n equals to 1, that is the highest at the middle of the box, and it was zero because the wave function was zero at the extreme end, that is x equals to 0 and that x equals to 1, that is the boundary condition. Now, if you plot this for n equals to 2, you can see this induces more oscillation, and obviously for a wave function it was also negative, but here it is becoming positive because we are plotting the modulus of psi of x t square. And again, here you can see that node is increasing. Then and oscillation is also increasing. For n equals to 3, you can see this will show this kind of plot because it induces more oscillation, something like that. And you can, plot all of these duals together for n equals to 1, n equals to n equals to 3, something like that. Okay. Okay, so basically what happens, what is the take-home message from this particular slides, that if the nodal point, corresponds to the region where the particle can never be found. So here you can see this one will be called as nodal plane, this one is nodal plane, this one is nodal point, sorry. Again, here this is nodal point, nodal point, node. So for n equals to 1, there is 2 nodal point. For n equals to 2, you can see 1, 2, 3 nodal point. For n equals to 3, there is a 1, 2, 3, 4 nodal points. So basically what is happening, number of nodal points are increasing if you are increasing the value of n. So as quantum number increases, obviously I have told you the oscillation is increasing, number of nodes increasing, and then the probability distribution become more complex, right? Here you can see it was very simple, where it was very easy. Again, it is becoming more and more complex if we will go for higher value of n, something like that. Okay. Okay, so this tells you that the probability distribution clearly demonstrates the quantum particle behave as a standing matter wave rather than the classical point particle. Okay, so here I'll end this lecture for particle in 1D box. So in next lecture, I'll start with the discussion of particle in 2D box, and again we'll drive the wave function, we'll calculate the probability density, and we'll see the effect of value of n that over the probability density as well as the wave function. Okay, see you in the next lecture. Thank you.